Okay, let me just record. So this is part 8, linear algebra. You have a question? Okay. So the first chapter is linear equations and the matrices. So linear algebra is basically how to solve a system of linear equations, and this becomes a topic when you have a large system like 1,000 equations with 1,000 variables or 1 million variables with 1 million equations. Then you want to find the easy way, a systematic way to solve it instead of just handling it one by one by elimination method or substitution method. We know how to solve those, but then you want to find the easy way to solve it by the machine, especially when you have the computer, you can solve it by the computer to write the code to solve it by the computer instead of doing it by hand. And that's why we need to learn the linear algebra. It tells you how to, use matrices to solve a linear equation, system linear equations, and there are a lot of properties of matrices that are consistent with the linear equations. So this involves the procedures to solve linear equations from the matrices. So you don't write down the variables in the equation, but just input all the numbers and handling the numbers in the way as if you were actually solving the equations. We're going to talk about a lot of properties of matrices, some of them are really straightforward, but it has a lot of properties that they need to know. Okay, let's just start from a very basic thing, how we define the matrix, for example. So the first section of chapter 1 is systems of linear equations. So the first thing is what is a linear equation? Suppose you have a bunch of variables, x1, x2 to xn. Those will be n variables that you need to know. They are unknown, so you need to solve those variables. And there are also a bunch of numbers that are given in the problem. We call them a1, a2, up to n. They're called coefficients, and then b a constant on the equation on the right. Okay, then you can write down this equation a1x plus a2x plus a3x up to plus nxn equals b. So that gives you a linear equation with n unknowns, n variables. So that's one linear equation. It is linear in the variable. Okay, x1, x2 to xn. All of them have exponents 1. So that's called a linear equation. And we only have one linear equation. All right. But you can write down similar equations in the same way as we have. And then you come up with a bunch of equations. For example, you can write another equation as a21 x1 plus a22 x2 plus a23 x3 up to a2n xn equals b2. So this equation, you just change those numbers, the coefficients, those a's, and b's, put some other numbers in front of the variables. You get another equation, and you can do it, repeatedly. For example, you can write down n equations like this. So this is called a system of m linear equations in unknowns. Okay, m. I'm sorry, I probably said that n should be m. So you got m linear equations with n variables. So you got the x1, x2 up to xn. So those are the variables, unknowns you need to solve, and you have m equations. The number of equations and the number of variables are not necessarily the same. Okay, in many applications, you may have the case when the number of equations is fewer than the number of unknowns. All right. Or the other way. And different situation can occur. You can have different types of solutions. You can have many solutions. Sometimes you can have a unique solution, or you can have no solution. All right, depending on the problem. Okay, so that's a system of linear equations. If the linear system has no solution, it's called inconsistent. Okay, no variables or no values for the variables can satisfy all the equations. So these equations are not consistent themselves. Okay. If it has a solution, then it's called consistent. So these equations are consistent. They can be true at the same time. That means. And the linear system is called homogeneous if B1 equals B2 equals B3, 2BM equals so everything on the right of those equations is 0. That's called homogeneous. Otherwise, called non-homogeneous. If any of those equations has non-zero on the right, then it's called non-homogeneous. Okay. So one of the easy thing you can see is a homogeneous system always have a solution. When you plug in 0 for all the variables, the equation is always true. So a homogeneous equation is always consistent. All right. So let's just look at some examples. So we have a linear equation 3x1 plus 2x2 equal to 6. And this is a consistent system because you can easily find the solution to this equation. For example, if we plug in 2 for x1, 0 for x2, you get the 2 times 3, which is 6, plus 2 times 0, which is 0. So you get 6 on the left and the 6 on the right. So you have one solution to this equation, but you can find, of course, infinite many solutions to this equation, as we know. So it is consistent. And it's not homogeneous because you got 6 on the right, which is not 0. All right. So this is a consistent, non-homogeneous linear system. Although it only has one solution, one equation, you can still call it a system. All right. And you can easily write a system which is inconsistent. Okay. For example, if we write, 2 more equations for x1, x2, you can easily make them inconsistent, right? Okay. So as I said, the homogeneous system is always consistent because if you put all the argument x to be 0, then the system is always true. Just imagine you get all 0 on the right. So then it always have the solution of x1 equal to 0, x2 equal to 0, and x and all the variables equal to 0. It will be a solution to the system, right? Any questions? I think this thing is pretty straight. You already know that. And there's nothing to learn about this, actually. So it's kind of review, but we're going to, introduce the concept of metrics later. And 2 linear systems are called equivalent if they both exactly have the same solutions. Okay. So, so it's actually just the one system. And the point is you can always use equivalent operations to change one system to another system and to solve it. To solve a system of linear equations is actually a procedure to find equivalent system, which becomes simpler each time we do it. Okay. So for example, we want to find the solution to a linear system, and this linear system has 2 equations. x minus 3y equals -7, and 2x minus 6y equal to 7. I'm going to use the method of elimination, but you can also use substitution method, as we know. In systems, linear systems of large numbers, large systems, if you have a lot of equations with a lot of variables, then you usually do elimination instead of substitution. Okay, so how do we do that? It's pretty straight, I think. You can easily eliminate x in the second equation by multiplying -2 in this first equation and then add to the second equation, right? If you do that, what do you get? So you get -2x plus 6y equal to 14, isn't it? And then you add these two equations, you can see everything on the left is just the opposite. So they cancel completely. So you're gonna see, you get 0 on the left, but on the right you get 14 plus 7, which is 21. So you get something inconsistent. So that means these two equations cannot be true at the same time. So the system itself is inconsistent, right? All right. So that's a simple example of inconsistent system. So another example is a system of 3 equations with 3 variables x, y, and z. We got the x plus 2y plus 3z equal to 6. 2x minus 3y plus 2z equal to 14, and 3x plus y minus z equal to -2. So we're going to use elimination method again to solve this system. So what you do is just multiply -2 to this first equation on both sides, and then add to the second equation, and multiply -3 to the first equation and add to the third equation. So then you can eliminate the x on both cases, right? So does it make sense? So it's easy to eliminate the x in the second and third equations from the first equation. Okay. So if you multiply -2 to the first equation, you're going to get -2x minus 4y minus 6z equal to -12. And then you add to the second equation, the -2x and 2x will cancel, and -4y and -3y will make -7y, and -6z and the 2z will make -4z. And the -12 and 14 will make a +2, isn't it? So that's the new equation we get after elimination. And then you can do it similarly in the third equation. If you multiply -3 in the first equation at third equation, so you're going to get the -3x minus 6y minus 9z equals -18. And then you add to the third equation, you're going to get 0 for the x, they cancel. And -6y and the positive y gives you -5y. And -9z and -z gives you -10z. -18 and -2 gives you -20, right? Yeah, it's easy to check. I mean, the detailed steps are not written here, but it's pretty easy for you. Okay, so then we end up with 2 equations with 2 variables. So now we eliminate the x in both equations, and then we can deal with the easier system. And before you do anything, you may want to simplify the last equation. If you look at the coefficients of the last equation, we get 5, 10, 20. So you can divide by 5 on each term of this equation, or -5 actually. So you're going to get 5 plus 2z equal to 4, isn't it? And then you can use that equation to eliminate either y or z in the equation above. Okay. And if you do that, you're gonna get a 10z equal to 30. Okay, for example, so we got the 5 plus 2z equal to 4, right? So if you multiply -7 to that equation, you're gonna get a -7y minus I mean, you're gonna multiply by 2, I'm sorry. So you're gonna get a 7y plus 14z equal to what? 28. Yes, 28, right? Multiplied by 7. So then you add to the equation above, the y's will cancel, and the 14z and -14z gives you 10z, positive 10z, and 28 and 2 add up 30, right? And then you divide by 10 on both sides, it gets equal to 3. So once you get z, then you plug in back to either equations, you know, to get y and x. So we have the equation y plus 2z equal to 4. So you plug in that, z equal to 3, 2z will be 6. So y plus 6 equals 4. So if you subtract 6 on both sides, you get y equal to -2. 4 minus 6, -2. And then you plug into the very first equation from the original system, y equal to -2 and z equal to 3. You can solve for x. So you get 2 times -2, that's -4. 3 times 3 equal to 9. So -4 plus 9 equal to 5. So x plus 5 equal to 6. And then you subtract 5 on both sides, you get x equal to 1, isn't it? Okay. So we have a unique solution to this system. And so that's the solution. That's the answer. Any questions? I guess this should be straight for you. Okay. So if you write down some intermediate steps from this example, we got remember we got a y plus 2z equal to 4 and z equal to 3. That's when we solve the z. Okay. Here we got those. So this is the new system that is equivalent to the original system. So solving a system of linear equations is actually writing down a equivalent system simpler to the original system, right? Okay. So that's one example, and the next example is a system of two equations with 3 variables. Okay, we got x plus 2y minus 3z equal to -4, and the 2x plus y minus 3z equal to 4. So you can easily see, you know, this system will have infinite many solutions. And for example, if you eliminate the x from the second equation by multiplying -2 in the first equation and add to the second equation what they get. So multiply -2 on both sides of this first equation, you get -2x minus 4y plus 6z equal to +8, right? And then you add to the second equation, the x cancels, and the -4y and the y gives you -3y, positive 6z and -3z equal to gives you 3z, positive 3z, and positive 8 and 4 gives you 12, right? And then we got -3y plus 3z equal to 12. We can simplify it a little bit by dividing by 3 or -3. I think we're going to divide by -3, so you're gonna get a y minus z equal to -4, right? And then you move z to the right side, you get a y equal to z minus 4, isn't it? Okay. So, yeah, z minus 4. Y will be z minus 4. Yeah, that's y. And then you plug back into the first or second equation, you're going to get y equal to x equal to plus z plus 4. So this is coming from plugging y equal to z minus 4 in the first equation, for example, and solve for x. Okay, so 2 times y, so 2 times y minus z minus 4, we get a 2z minus 8. So 2z and -3z becomes negative z. And -8. move to the right becomes positive. So that's negative 4 plus 8 is positive 4. So you get x minus z equals to positive 4. So if you move z to the right, you get x equal to z plus 4, isn't it? So then we have the solution of this, and z can be any real numbers because we only have two solutions and we got three variables. So one of the variables can be chosen arbitrarily. So this system has the infinite solutions because you can choose z arbitrarily. Once you choose any specific value of z, then you get the values of x and y. And if you change z, you get another solution, right? Okay. So these examples suggest that the linear system may have a unique solution, as we did in the second example, no solution in the first example, or infinite solutions as the last example. Okay, we have seen that in Math 112, didn't we? Right? Okay, we know those things. Okay. So this kind of situation can be easily understood in terms of graphing. If you draw the graph of each equation, for example, if you have a system with two variables with two equations, so that will give you two lines on the plane, isn't it? So a1x plus a2y plus c1 is one line if you draw it, and b1x plus b2y equals c2 as another line. Then you just look at the relationship between the two lines geometrically. So this is an algebraic problem can be converted into a geometric problem, which is much easier to understand. So the solution must line on both lines. Okay, so then you can see whether these two lines whether have an intersection or not to determine what kind of solution the system is. Okay, so then you have three different situations. If the two lines coincide, then this two lines actually becomes one line. You have intersection of those two lines infinite many points. So that gives you infinite many solutions, isn't it? If the two lines intersect at exact one point, then you have a unique solution at the intersection. And if two lines are parallel but do not intersect, then they never intersect. You don't have any solution and no common point between these two lines, right? So you can understand everything in terms of geometry, and this is a very important thing to know. Okay. Now, this is a case of two variables with two equations. So suppose now you consider three equations and three variables. Then the geometry becomes a little different because now each equation actually gives you a plane. An equation with three variables, a linear equation, gives you a plane. Okay, well in different space. So we got three planes. Then we want to see the relationship between those planes. Again, it will end up with three possibilities. If all three planes coincide, not necessarily coincide, but if they all intersect at one line, then it has infinite many solutions. If planes in this intersect on a line, okay, that's what I said, all coincide. You have infinite many solutions, and those planes can intersect at exact one point, and then you get a unique solution. They just no parallel or anything. If the two planes are parallel and do not intersect, then no solution. So if you get two parallel planes, then they never intersect. So in that case, you get no solution for the system. So this is the situation here. You can see, unique solution in here, infinite solution, just look at the sections of those planes, and no solution, right? So, but if you want to consider, more than 3 variables, then it will become hard to visualize, right? So this is the case for linear systems. In the case of nonlinear equations, although we are talking about the linear equations and the linear algebra, you still want to know that the situation is very different for nonlinear systems. System of linear equations may have more than one but less than infinite solutions. For example, if we think about 2 circles, then you can have no solution. So 2 circles, each circle is a quadratic equation, isn't it? Of 2 variables. So these 2 circles can be apart, so no solution, no intersection. Or one solution when they are in tangent, or 2 solutions when they intersect at 2 points, or infinite solutions if they coincide, right? So non-linear equations are very different from linear equations. Just keep in mind. So this is the first section, I believe. I guess we just stop in here. Everything it's pretty straightforward. Any questions? Well, I guess I'm going to stop here and